It's like an hour. So we decided that what we did before was actually fine if we interpret it correctly. Basically, what I was starting to work on here was actually k equals to 2. And what we've seen through this little calculation was that we had brackets of brackets over here, which is actually in the second derived algebra of L. So that's basically showing that L mod I, the second derived series of that, is second derived thing of L plus I mod I, which is what we wanted actually. L equals 1. Let's see here, what do we have? Did we figure it out yet? So this would be, so L mod I prime would just be what? Stuff like what? I guess just brackets of quotients, right? It's just x plus I, y plus I for x and y and L, and obviously I is the ideal. That's something in L quotient I prime.
Mm-hmm.
And then on the other hand, this would be something like, something in L prime would be, oh, this isn't right either. L prime wouldn't have, this is not L prime.
Right, that's L prime.
Let's try this again. L prime would be something like xy. So xy plus I would be something in the top. So that's the representative. And then you do plus I. And so this is kind of stupid. That just reduces to x comma y plus I, right? Because like adding 0, essentially. That's that. Whereas this, through a little bit of algebra, the definition of the bracket actually gives you that.
Right.
So they're the same type. Now this is not quite a proof. I'm just arguing plausibility at the moment. The proof that textbook has here, he basically he doesn't actually have the proof. He just suggests. So I will suggest this as an exercise. He says you can look at the canonical homomorphism from L to L mod I. Look at the canonical homomorphism, the projection, right? And then, or you can prove it directly by induction on K. So, oh, because, yeah, you see it. So, the canonical homomorphism, basically think of this as being like the homomorphism. Then, oh, duh. So the image, so basically pi of L is equal to L mod I.
Right.
So, oh man, why not just, dang it. So of course, pi of L to the K is equal to, pi of L to the K. Right? And so this is L mod I to the K, whereas this is L of K plus I. Because the canonical, what is pi? Pi of L, pi of x is just equal to x plus I. That's the canonical homomorphism. I stupid. Let's see here. All right. Okay, finally, let's move on with it. If L mod I is solvable, then we have what? So L mod I is solvable. Yeah, L mod I to some m is 0, right? Which tells me that L mod I well, that tells me that Sorry, I missed something. Okay, so
M plus I.
yeah, L to the M plus I mod I is also equal to 0, right?
Great.
Which says that what? The mth derived series of L plus I is just equal to I again. I mean, that being 0 means that the mth derived series is again in an I. Therefore,
Since I is solvable.
Lm is a subset of I. Okay. And then he says, if I is also solvable,
M is solvable. Oh, it's 0.
then the kth, so for some k, is 0. And,
Oh, M to the K is 0.
right, hence, here's what he writes. He's L of m to the k is a subset of I to the k. Oh, right. It's that subsetting again.
Yeah.
This time, folded, but yeah. And that's 0, okay, so. And he says, now you can convince yourself,
That is M times K.
yeah, m plus k actually.
Oh, M plus K.
You can convince yourself, there. There's some non-standard spelling.
Nice.
That'd make a good homework problem right there.
Yeah.
Earlier. And so that shows then that L is solvable. But of course that's equal to 0. So therefore L is solvable. Okay, so that brings us to proof of part C. By the second isomorphism theorem, we have the following. We have that I plus J mod I is isomorphic to what? To J mod the intersection of I and J. Now what was our assumption here about I and J? Anything in particular? Just that I and J were solvable ideals. That's it. So this is this right here, what I just wrote down, is the second isomorphism theorem. All right. So it is solvable by lemma 4.4a. What is solvable? Is quotient solvable?
Are we doing part C now?
Yeah, I'm working on C, yeah.
So I plus J.
Oh, that's right. I plus J is solvable?
Here's what C says.
Oh, we're trying to prove I plus J is solvable, right?
Yeah.
Right. We know that I and J are separately solvable, right? Now, why is he using... He says, so it is solvable by lemma 4.4a. He's saying this is solvable. I mean, J is given to be solvable, right? Yeah. Why is I intersect? since I is also solvable, part B of this lemma implies that I plus j is solvable. Suppose L is an ideal, that I and L mod I are solvable, then L is solvable. I think he's thinking of L as being, I think L is I plus j. Okay? So think of L as being I plus j, right? Our goal is to show L is solvable, right? Then part B said that if you know that I is solvable, and L mod I is solvable, right? Then that implies that L was solvable, right? Now, I was given to be solvable in the assumptions of part 3, right? So we just need an argument that I plus j mod I is solvable. Okay? But by the second isomorphism theorem, I plus j mod I is isomorphic to j mod I intersect j. Now, isomorphism means in particular this is a homomorphic image. But the inverse image, it's also invertible. I mean, it goes back. Yeah. So this is the homomorphic image of that as well.
Right.
So if we can, basically what it boils down to is, if we can convince ourselves, we just need to show that that's solvable, then we're done. So the question is, why is that solvable? And we're given that I and j both solvable, right? I would point out to you that I intersect j is a subalgebra. Because the intersection of subspaces is a subspace. As I've said many times, the reason I did not give an A in the fall 2013 linear algebra semester. No one could solve that. Maybe one.
Sad.
Very sad. I wanted to give some of those students A's. I really did. Anyway, I intersect J, subalgebra. But it's what else is it? It's, I mean, that's a subalgebra. It's a subalgebra of I, and it's a subalgebra of J.
Right.
Okay. Oh, but we know subalgebras of solvable are solvable, right? So I know that algebra, and in fact this is, solvable, right? But if I have solvable, mod solvable, do I get solvable? I don't remember us saying that. So how do I know? He's like, so it is solvable by lemma 4.4a. I know 4.4a gives me that I intersect j is solvable. 4.a said that, oh, every homomorphic image as well. Is this the homomorphic image then? You see? So this, maybe it's the homomorphic image actually, though, right? So like, you can take pi from j to j intersect I with j, right? Mm-hmm. So this is equal to pi of j. So it's the homomorphic image of j, which is solvable. Therefore, that's solvable. Therefore, this is solvable. Therefore, that's solvable. Therefore, that's solvable. Therefore, that's given to be solvable. Therefore, L is solvable. Therefore, I plus j is solvable.
Yep.
Yeah. This is why we should spend much time thinking about isomorphism theorems until they become second nature. We unfortunately in most undergraduate curriculum don't have enough time to spend on isomorphism theorems so that students can get comfortable with these things. But anyway. Oh well. right, so that brings us to what? Where were we? So that proves lemma 4.4. Corollary 4.5 then. Excuse me. Corollary 4.5. Let L be a finite dimensional Lie algebra. Right. There exists a unique, solvable ideal of L containing every solvable ideal of L. Like, does that make sense? What about SL2C? What about...
I feel like it's kind of like the analog of the maximal ideal thing that we did in abstract 2.
Right. Yeah. This should be like that, that's right.
But we never said there necessarily exists one.
Let's see here. This one... I mean, what does it mean if L is not solvable? Right. Oh, maybe if there is no... But it says that there exists. Doesn't that mean there has to exist a 1?
Mm-hmm.
Is 0... Oh, maybe sometimes 0 is the only solvable ideal.
Maybe.
Is 0... Yeah, the set containing 0 is a subalgebra. It's definitely an ideal.
Yeah.
Its derived series is 0, so it's...
It's true.
Yeah, 0.
They're always
The trivial subspace is automatically a solvable ideal. So I guess every algebra has that. So even though the special linear algebra of SL2C does not have a it's not solvable, and I don't think it has a trivial. I don't think it can it have a non-trivial ideal which is solvable.
SL2C.
I guess a billion implies solvable, yeah? Because to say it's a billion means that L of 1 is 0.
Right.
And certainly one-dimensional subalgebras are abelian. Because the bracket of any vector with itself, a scalar multiple of itself, is 0. But it must be then. Yeah, you can find an ideal which is solvable, even in SL2C, but it then must be the case that, in view of the lemma we just went through, it must be, yeah, I is solvable, but L mod I must not be solvable in that situation. L mod I still has all that brackets which go back to what they started with in SL2C style. Okay. So you said this is like the radical ideal notion, or this is like what? Maximal ideal? Yeah. Here's the proof. Okay, so proof. Let R be solvable ideal of largest possible dimension. Alright. Suppose I is any solvable ideal. lemma 4.4c, what do we know? We know that r plus I is what? Let's see, r plus I, it's, hey, this is the sum of two solvable ideals, is a solvable ideal. Right? Now, R is a subset of R plus I, right? That's just, that's linear algebra, that's nothing, that's just,
Yeah.
if you add 0, x is equal to x plus 0, 0 is an I, so x is an R plus I for arbitrary x, so x is a subset.
Right.
And we also, and hence what? The dimension of R is less than or equal to the dimension of R plus I, because, well, if it's a subset, then any basis for the subset, you know, be extended to a basis for the superset. Anyway, we choose R, but we chose R of maximal possible dimension. Therefore, we must have that the dimension of R is equal to, right? But we need, by maximality, the dimension of R equal to the dimension of R plus I. So what's that say? Oh, hence, R plus I is equal to R. So I is contained in R.
Right.
And what we're trying to prove, there exists a unique solvable ideal of L containing every solvable ideal of
So we
L.
should do uniqueness now.
Hmm.
Do you not do uniqueness?
Hmm.
Can we get away with not doing uniqueness?
He does not have a proof of uniqueness here. Hmm. I mean, that's not added by me. It says unique in there.
Yeah.
Let's see here. If you had two, R1 and R2.
I think it's implied when you say any solvable ideal. If I is any, I could be. You could say it's.
Oh yeah. So if R,
right?
but if R1 and R2 were both of largest dimension,
Right.
then
I is contained in R, and it would be the same thing.
So we have dimension R1 equals dimension R2,
Yeah.
and by our previous argument,
Yeah.
R1 subset of
It's
R2,
kind of hidden in this argument.
and R2 is a subset of R1,
Yeah.
so therefore R1 is equal to R2. Unique.
Yeah.
Ah, thank you.
I think it's there. It's just kind of hidden.
Yeah, I don't think I can accuse him of not. It's basically, it's one of these things like it's obvious, so I'm not going to write it,
Yeah.
which is fine. Number 8. Okay, and then this actually leads to something very interesting. So the largest solvable ideal has a name. Definition. The largest solvable ideal is said to be the radical of L. Radical of L, sometimes denoted rad. The radical will turn out to be an essential tool in helping to describe the finite dimensional Lie algebras, and it also suggests the following definition. So while we're on this, I told you guys about this last time we met, but here it is. A non-zero finite dimensional Lie algebra is said to be L is with L Lie algebra with the dimension of L less than infinity, is said to be semisimple, right? If it has no non-zero solvable ideals. That is, if the radical of L is 0. So he points out at this point that SL2C is semisimple. And the reason for the term semisimple is revealed in section 4.3 and also here. But what we were looking in Fraley?
I had something interesting for you.
Oh, okay.
We talked about the radical here in this problem. I wonder if the ideas are the same.
Let's see here. Let R be a commutative ring and an ideal of R. Show that the square root of n, such that the nth power of n is an n for some n and z is an ideal of R. So it's called radical of n. Yeah, I think that has more to do with. I think this is a different.
Different thing.
I think it's different, slightly different use of the word radical.
Yeah.
I mean, here it's a play off that being like a square root is a radical.
Yeah.
That's a good question. Is this the same use of the word? It may just be an analogy to the algebraic structure here.
Yeah.
I mean, something like the nth power is 0, right? It's solvable. I do think they're connected. I think you're right. But sometimes the wording. Be careful. I mean.
Yeah. This is also talking about the radical of an ideal instead of the radical of something that's not necessarily. Well, it's the whole set, I guess. So it is.
Yeah, I mean, L is always its own ideal, but yeah.
There might be some.
Yeah, but I cannot say with authority where precisely it's the same in difference. If you ask me to compare and contrast, I can't do that off the top of my head at the moment. But all right, so then that brings us to lemma 4.7. So we'll be talking a lot about semi-simple versus solvable and all that going forward here. This is page number 9. Yeah, I realized that landscape is the way to write for this kind of thing. I might start. Maybe I'll start. Maybe I should always write notes in landscape for this reason. Maybe it's better to have landscape notes to project, but all our projectors are set up the other way. But if you think about rooms, it would make more sense to have landscape projectors in terms of the usable visual space. But anyway. I am quite certain that the way we have things configured, and not just here, but many places, is not optimal. Lemma 4.7. Oops, now I'm doing black. Fine, I'll go back to purple. I feel guilty. All right. At least my purples are good. If L is a Lie algebra, then L mod the radical of L is semi-simple. In other words, once you calculate the radical, then you can take the quotient, and what you're left with is semi-simple. Of course, in the case that L is, trivial case, if L is semi-simple,
It's obviously.
then L mod 0 is L,
Yeah.
which is again semi-simple.
Uh-huh.
Encouraging. On the other hand, if the algebra itself is solvable, then it is its own largest. Then the maximal ideal is the algebra itself,
Right.
and L mod L is 0. So anything in semi-simple, and that is the trivial ideal, in sort of a vacuous sense. But so that's encouraging. Some extreme cases.
Yeah.
Here's proof. Let J be a solvable ideal. J bar actually uses. I don't know why he's doing J bar all of a sudden. It's kind of weird. Be solvable ideal of L mod radical L. Right. By the ideal correspondence. By the ideal correspondence, which is that thing I asked you guys to think about at the end of one day, there is an ideal of what? An ideal J of L containing the radical of L, such that J bar is J mod the radical. This goes back to this correspondence between ideals section here. Oops. Well. Not sure I can get it in focus or not, but here it was. He basically says, if I is an ideal of the Lie algebra L, there's a bijective correspondence between ideals of L mod I and the ideals of L that contain I. The correspondence is as follows. If J is an ideal of L containing I, then J mod I is an ideal of L mod I. And conversely, if K is an ideal of L mod I, then the set J, Z and L such that Z plus I is in K, one can readily check that J is an ideal of L and J contains I. And these two maps are inverses of one another. Yeah, we went over this another day, but it's a little rusty. Anyway, he's using that now in this proof of lemma 4.7. So he's basically saying, okay, so if it's a solvable ideal of the quotient, there has to be a solvable ideal of L, J, that contains the quotienting radical,
Right.
such that J bar is the quotient of J by the radical. And then what? By definition, rad L is solvable. And so we have what? We have radical L solvable, right? And we have J bar equal to L mod rad L solvable. So I think by part B of the lemma implies what?
So,
Yeah. Oh, I'm sorry, I'm an idiot. The radical is solvable, and this is solvable by hypothesis. Therefore, it's not L that goes there. I was like, why? I shouldn't be able to say that L is solvable. This is not that general a result. I mean, if L was always solvable, then most of what we're saying wouldn't be interesting. I mean, this is supposed to be a J. This is a J, not an L. This implies then that J is solvable. Right? But J is contained in the radical of L, right? Hence, J is a subset of the radical of L, right?
Great.
Thus what? Therefore, J bar equal to 0. Because J bar was the J mod. Yeah, so if J is a subset of radical L, then, yeah, it's in the 0 for the quotient, and so it's 0.
That makes sense.
But what have we shown then? We've shown that an arbitrary ideal
Has to be 0.
has to be 0, which then it follows, therefore, L mod radical L is semi-simple. All right. So that brings us to section 4.2 on nilpotent Lie algebras. So we've got about a page to digest there, and then we have the look ahead section, and then we have subalgebras of GLV, where we start getting into some of the things which build the representation theory. So chapter 5 actually gets away from this kind of, well, I mean, what we've been doing is important, but it's not the machine of representation theory yet. It's just kind of underlying theory. So when we meet again Thursday, I'll start here. So anyway,
Sounds good.
very good. I guess I've got some stuff to upload.